Okay, today I thought we'd look at one of my old projects I made. I think probably in about 1987-ish, 88 maybe, around that time. At the time I had this ICOM receiver. I think it was an ICR 7000 if I remember rightly. I think it was just VHF only. I think it covered 30 megahertz to about 1.5 gigahertz, but I can't really remember because it was such a long time ago. I think I bought it in about 1985 roughly, and so I was primarily obviously only using it on VHF and UHF, and that was in the days when cell phones were analog, of course, and you could listen to them on 900 megahertz, which is quite fun. There's a hell of a lot of stuff on VHF in those days. You had the Police on 450 megahertz with their little repeater a few miles away, and of course on VHF they had other stuff as well. Then there was all sorts of PMR stuff and radio amateurs, of course, on 2 meters and 70 centimeters. And this particular receiver, although it was a very nice receiver, it was kind of a bit deaf, so I built this little preamplifier for it, and the idea being that it would cover basically the range of that receiver, which it did very well, and it improved the sensitivity considerably. It would bring a noisy signal up to a less noisy signal, if you like. So yeah, and I've used this basic design similar design to this in many other projects over the years. But we can look at the circuit of it, and this is basically the circuit. We've got the input coming in there on an N-type connector, and then we've got a DC blocking capacitor, and that's not critical. It could be anything from about 1N NF roughly, anything that's going to pass VHF fairly well. And then, because I only wanted to use it from over a certain frequency range, I built a little high pass filter in it. And the other reason for that is this transistor's got an enormous gain at any frequencies below about 30 megahertz. The gain is phenomenal, so you don't want it to be amplifying everything that's coming in here. So you really want to put a high pass filter in it, which limits, I think, anything, cuts off about 3 dBs at 30 megahertz, something like that. So that's a very simple high pass filter, which I just designed by trial and error really. Didn't really have any access to design stuff in those days. So, and after that it's DC coupled again to the base of the transistor, and you've got the biasing components on the base. There's one there down to earth, and the other one goes up to this point, which is at approximately 10 volts. You have to bias, the transistor likes about 10 volts on its collector, so you choose your biasing components and that resistor there to get 10 volts at approximately 20 milliamps, I think, in this circuit. And there we've got an inductor, which is fairly important in the collector circuit, and that presents a high impedance across that frequency range that I was using it on. And it's a little toroid, it's a tiny little toroid. I think it's a T2012, if I remember rightly, with a few turns of wire on it. And after that we got a coupling capacitor, which is again about a 1N DC blocking, that goes to this bit here. And because this circuit had quite high gain at certain frequencies, there was a danger of overloading the receiver. So I did put a little pad in there, if you like, 3 dB roughly, I think it was, pi attenuator. And after that you just got another coupling capacitor to the output. And the only other parts that were included, to try and make this as flat or fairly flat as possible across its frequency range, I included a negative feedback circuit. And I got this idea for negative feedback from an old Avantech amplifier I found in the scrap heap at work. And nothing wrong with the amplifier, but the power supply had blown up. It was a very nice amplifier until I blew it up. But never mind. And what they did in there, and what I've done here, is they have basically you're feeding back a signal from the collector to the base, and you have a coupling capacitor, which is not critical again, and then an inductor which optimizes the coupling across the frequency range. You want more coupling at low frequencies to reduce the gain at low frequencies, because this transistor's got enormous gain at lower frequencies, and less coupling and less effect at high frequencies. So, and the other component would be the resistor, which optimizes the amount of signal that's going back through there, because this transistor was a 2SC3358. It's got an FT of 5 GHz and very low noise, about 1 dB noise figure at 1 GHz. So it's a very nice little transistor, and fairly cheap if I remember rightly. And considering this is like over 30 years ago, quite a good transistor, and I would still use it today if I was building a circuit like this. So, having said all that, let's have a look at the actual box and the components in it. Okay, so this is the little box I built it in. It's quite a challenge in those days to get everything in there, because I didn't have access in those days to surface mount components. So I was having to do the best I could, really. And in fact, some of the actual capacitors, like that one there, and a couple more on the board, they're not surface mount capacitors as such. They're resin dipped capacitors that I've broken the resin off and unsoldered the wires and turned them into surface mount components, because partly because of the high frequencies involved, and partly because they took up less space like that. So I think that was originally an 8 watt resistor, like the one down there. But anyway, this is the input, N-type input, and goes into the coupling capacitor down on the circuit board. And then these are the coils, 2 coils for the high pass filter. Getting a bit closer. So yeah, those are that's the high pass filter, those 3 components. And tantalum capacitor, which hasn't exploded or burst into flames yet, which is quite amazing. And then you've got the coupling capacitor into the base of the transistor, and you can just about see the little transistor down there. You can see the 8 on the end, 2SC3358. It's got 4 legs on it, 2 earth pins to keep the inductance down, and a base and a collector, obviously. And this is the feedback network I was talking about. You've got a coupling capacitor there, no idea what value it is, about 1 NF, it's not important. And then a feedback resistor, which is actually surface mount, so I probably added that later on. And the coupling coil, which is that coil there. But anyway, and apart from that, and the camera's shaking because it's on maximum zoom, I think. Yeah, that's the inductor on the collector, on the toroidal core, and that's the 100 ohms that goes to the supply. And the pi attenuator is down there. There's 3 resistors, 8 watt resistors. Those are the 2 that go to earth, and there's another one in series, or there should be. Yeah, I can just about see it down there. and then another coupling capacitor to the output N-type socket, N-type plug, because the receiver had an N-type socket on the back of it. And this is the power supply wire coming in there, and that's about it really. I etched all my own boards, as I still do. Always quite a challenge to make something this small, but worked very well in this little box. So as you can see, it's quite a small box. So I think now I'll just put it on the spectrum analyzer and we'll have a look at how it performs. It doesn't perform as quite as well as I'd hoped. It's not as flat as it could be, but it is fine for what it was used for. Okay, so here's the screen of the spectrum analyzer, and at the moment it's not connected in circuit, but what I'm doing is I'm outputting a signal from the tracking generator output into the input of the analyzer. In other words, the tracking generator sweeps the signal generator at the same frequency as the spectrum analyzer is looking at. And I've also got 6 dB pads on the output from the tracking generator and the input to the spectrum analyzer, because it seems to improve the response of the system. There's, I think, some impedance inaccuracies on the output of the tracking generator and the input to the spectrum analyzer. They're not perfectly 50 ohms, so I'm padding them with 6 dB on each port. So we're sweeping from, I believe, 0 to 1.5 gigahertz, and I've just got it wired straight across at the moment with no amplifier in circuit. So I have to first of all normalize this. So normalizing sets a baseline measurement which should be 0 dB. So anything above that will be visible. So now I want to connect this in circuit, and I'm going to have to do that fairly quickly. So unplug that, plug the preamp in, and connect the power up to it. And there we go, we now get a response of the amplifier. If I go down to marker 0 megahertz and then gradually move it up, you can see there we've got the frequency and the gain. The 20 megahertz got minus 3 dB gain, which is what I wanted, as this was a VHF UHF amplifier. Now we're coming up here, and this is where the low pass filter, high pass filter, starts to come into operation, or you get your effectiveness of it. So anyway, we've got there at 48 megahertz, or if we drop it down a bit, it should be okay, 30 megahertz, 12 dBs of gain, which is fair enough. And then we go up a bit, and then we've got a bit of a peak there at 44 of nearly 15 dB. Yeah, 66 has got 15 dB. Don't want any more than that really, otherwise you'll overload the receiver on strong signals. And then it sort of meanders around at about 13 dB. There's 250 megahertz. That's about what I wanted really, that sort of gain level. And we go up to say the 430 megahertz amateur band, 13 dB still, and then it starts to climb a bit, which is interesting. At 500 it's nearly 15, and 600, 15 nearly, 700, it's quite a peak there at 700. That's not a problem. Signals tend to be a fair bit not too strong at those frequencies anyway, except for TV signals, it might pick up in those days. And then it sort of starts to tail off, and 800 it's still 14, and get up to 900 and What were the cell phones on? They were on about 930 in those days, or around that area, so it's got 13 dBs of gain at 930 megahertz, and it will gradually roll off now as the gain of the transistor drops. And at 1 gigahertz we've got 12 dB, which is fine. I never listened to anything above a gigahertz. It wasn't anything worth listening to. There's a 23 centimeter amateur band, but I never heard anything on that. Anyway, we'll just continue up a bit, and now it's sort of really starting to drop off to 8 dBs at 1.3 gigahertz. And if we really want to go all the way up to the top of the scale, 5 dBs at 1.5 gigahertz. So all in all, it did the job. It's not as flat as perhaps I would have liked it, but if I'd fiddled and fiddled for hours and hours, I might have got it a lot flatter. But it worked fine for what it was. Anyway, I think that's about the end of this, so I hope you enjoyed it, and see you next time.